Hi everybody, Amanda Pilz here with Chemistry 125, here to do today's lab number 8 in our last lab. So today we're going to be doing an experiment with instant ice using really cold water. So let's jump right in. The materials we're using for today's lab is I have 3 bottles of purified water that I've put in my freezer for about 2.5 hours, so they get really cold. You don't want to use water with impurities, so you don't want to use tap water. It should be purified or distilled water. I have a cup of ice, and I have this little clear ramekin so I can do one part of this experiment and you can see through with the transparency. So right here I have one of my water bottles, the purified water that I've put in the freezer for 2.5 hours. The goal is to get it really cold below its freezing point, which is 0 degrees Celsius, without actually turning it into ice. This process is called supercooling. Supercooling works because as long as we don't disturb the water, it can go below its freezing point without turning solid. The water stays liquid because it hasn't had a chance to form any ice crystals. Now let's see what happens when we disturb the supercool water. I'm going to gently tap the bottle and see if that's enough to start the freezing. I don't know if you can see this, but some of these ice crystals formed in here. So you can see that's more hardened water there. When I disturbed the water, it caused a small disturbance that is known as nucleation, where the water molecules begin to arrange themselves into a crystal structure. So once that freezing starts, it continues rapidly until the whole bottle is frozen. Now let's try another way to trigger the freezing. For this part, I'm going to pour some of the super cooled water onto the ice cubes and see what happens. So I've got another bottle here that I've frozen for a few hours. I'm going to open it up. And here I have my ice cubes, and let's pour this onto, well, that's not working. Perhaps this is not cold enough. Okay, let's try one more experiment with our super cold water. So I have this clear ramekin. I'm going to open up another bottle of our super cooled water. Pour it in here and try to take one of our ice cubes to see if we can freeze it in place. And I don't know if you can see that. Some of the ice crystals are forming there. And I'm just holding this in place until it has completely frozen. So why does this happen? Well, the chemistry behind it is that normally water freezes, as I mentioned, at 0 degrees Celsius under standard conditions. However, pure water can be supercooled below its freezing point without turning into ice if it remains undisturbed. In the instant ice experiment, you use purified or distilled water and carefully cool it down to just below its freezing point without disturbing it. Distilled water lacks impurities that would normally trigger freezing, and the smooth container and gentle cooling keep it in its liquid form. For ice to form, water molecules need a structure to start building ice crystals, and this is called the nucleation site. In supercooled water, nucleation hasn't occurred yet because the water is undisturbed. When you tap the bottle, pour water over ice, or introduce a small impurity, like the ice, you trigger nucleation. This provides a site for the water molecules to start aligning into a crystalline structure, causing the entire liquid to solidify rapidly. As the supercooled water turns into ice, it releases latent heat, and this is energy that's released during a phase change. This energy might raise the temperature of the ice slightly, but doesn't affect the process significantly because the freezing happens so quickly. Once nucleation begins, a chain reaction occurs where the water molecules rapidly align with the growing ice crystal structure. This fast alignment is why the liquid appears to freeze instantly. And that is how the ice experiment works. So I hope you enjoyed this positively fabulous last experiment of supercooling and ice formation.